time is up. So welcome to the seminar of this afternoon. And today we are very happy to invite Zhi-Wei Wang from the University of New York to give us a talk. And let me first briefly introduce Zhi-Wei Wang. So he is a postdoctoral researcher at the University of New York in UK. So he received his PhD from the University of New York in 2020, and subsequently he conducted postdoctoral research at the University of Lethbridge in Canada, and then the University of Warwick in UK, and also the University of York in UK. His research primarily focuses on the theoretical work regarding black hole thermodynamics and dynamic spacetime and quantum gravity phenomena. Now, his relevant research has been published as the first author in journals like Nature Astronomy and Nature Communication, PRD. So today he will give us a talk about the equality of ADM mass and the generalized Komar energy in asymptotic flat dynamical spacetime. So let's welcome.
Thanks for the introduction from Professor Wang. And okay, let's begin. Today I will talk about the relationship between ADM energy and Komar energy in dynamical relationship in stationary spacetime for asymptotically-flat. Stationary spacetime is already been known clearly. So, and we try to find the relationship in asymptotically-flat dynamical spacetime. And this is the result, final result we found. You can find the ADM energy equals generalized Komar energy we will introduce, and the manners for asymptotic-flat spacetime is assumed to be zero, even for stationary spacetime. So, and of general relativity, there are two popular global energies well accepted. Well, one is the ADM energy, which is based on the Hamiltonian formula, which is developed by Noether, Zhi-Wei, and Missner. This is why it's called ADM energy. These three people formalism, which meaning Einstein combine time and space, but this also makes it very hard to define energy in general relativity in the background, because you don't have a real reference when you define energy. So these three people use the three formalism split the four-dimensional spacetime into a series of three-dimensional space-like hypersurface, Hamiltonian energy on each hypersurface energy. Because they developed the Hamiltonian in general relativity, and we know the Hamiltonian corresponding to energy. So their definition is naturally to be thinking as the physical energy. And they do this work in around 1960s. So you can see it's take nearly 40 more than 40 years from you have general relativity to you have a well accepted energy definition in defining energy in general relativity. On the other hand, at the same time, almost another person called he also developed the definition. When he did the Einstein tensor and before him, ADM energy is based on, because it's based on 3+1 formalism. So in his expression, this is the Jij, is the reduced matrix, which is not the four-dimensional, the matrix for the four-dimensional spacetime. It's the matrix on each hypersurface. So it's like a projection of the four-dimensional spacetime onto a three-dimensional hypersurface. So I and J, is variable like 1, 2, 3. is only 3 number. If I write J nu in this lecture, then it's a 4-dimensional matrix, which meaning the indices run from 0, which is a time coordinate. 0 is clear, and you can also see, the ADM energy is based on it's not covariant derivative, but we know in general relativity, in fact, the symbol we really prefer is derivative. So this is some limitation of or some not very elegant part of the ADM energy definition. But it's true both for stationary and dynamical asymptotic spacetime. So it's both for stationary and dynamical. On the other hand, Komar proposed an energy definition based on the Killing vector. In general relativity, Killing vector is a kind of vector which you use to label the symmetry of spacetime. So you can see global energy is based on some symmetry of the spacetime. For example, for timelike Killing vector, have a timelike Killing vector. This meaning this spacetime have a kind of symmetry on the time direction, which meaning at each moment the spacetime trivial example or easy understanding example is for example, if you have one black hole or any interaction with other black hole or other matters, then you have a symmetry because this black hole, for example, if it don't have or even it have a rotation, it looks the same at different momentum. Like at one momentum, like t0, the matrix look like this, and at another time, if you wait for like 1 year or something like this, it still look like this because it don't have any interaction with other place. So for such kind of spacetime, you will have a timelike Killing vector which label this kind of symmetry, and he defining this his energy based on this symmetry, this Killing vector, which can be written into a covariant formula. He write it as an antisymmetric derivative, but because Killing vector have another property which is is antisymmetric covariant derivative equals is just derivative because it's a Killing vector. But this is only true for stationary case because only stationary spacetime have this kind of symmetry. You can find or have a Killing vector, and if you change this to for example, you can also have angular Killing vector, which label a kind of symmetry in the angular direction of the spacetime. You can also define angular momentum based on this similar formula. So this is another well-accepted global energy definition. And you can see, because this energy definition is related to the symmetry of the spacetime. So later, after he proposed this energy definition, people found, in fact, his approach is based on Noether charge, Noether theorem. Noether is one of the most Noether theorem is one of the most important theorem in physics, which meaning when you have which claims when you have some symmetry, you have some conserved quantities. So then, after some years, people understand both of these two global energy definition is based on some very solid, physics philosophy. One is based on Hamiltonian, the other one is based on Noether theorem or symmetry. So, but they look, totally different. One is covariant derivative, one is, ordinary derivative and the reduced matrix. But if they give the same answer for same spacetime, then people will ask, they look entirely different, but they give the same answer for stationary asymptotic flat spacetime. Maybe they should have some relationship. After about 20 years, until 1978, Beijing first time proved, for asymptotically flat stationary spacetime, because Komar energy or Komar mass only defining for stationary spacetime, it requires a Killing vector. Beijing proved, they for stationary spacetime they equal to each other with some kind of asymptotic conditions. Like asymptotic, of course, you need to approach some flat spacetime at a special infinity. So yeah, this is one of the most important, things people found. And then until now, people have lots of try, but because the Komar mass or Komar energy itself is defining based on Killing vector, so people wonder, whether they have some, maybe wonder, they have dynamical, or they have relationship in dynamical space-time, but there's no rigorous proof to show their relationship or find the relationship between them. There are some more, but not too much. Very few, I think, based on my understanding and my research. So we want to find, whether first, Komar energy can be defined in dynamical space-time. Secondly, whether these two global energy definition also have a relationship, if Komar energy can be defined, have a relationship in a dynamical asymptotically flat space-time. So to finish this, we need first defining, first generalize Komar energy to dynamical space-time when there's no Killing vector. And also dynamical space-time is much more, complicated than stationary case. Stationary case is more easy to deal with, is more ideal, So, and this is the main result we achieve, Firstly, we need to generalize, Komar energy definition. In fact, if you study the Noether charge, because now we understand the Komar energy is a kind of a Noether charge, you find, you can always define some conserved current in general relativity based on vector, which meaning you just make, antisymmetric derivative and then take another covariant derivative. This will always be a conserved flux, even locally. If you make another covariant derivative for this vector, because the symmetry relationship and branch identity and so on, it will always equal 0. Which meaning if you integrate this term, this expression in a volume, for example, we just make an arbitrary volume. This volume is 4-dimensional in space-time, and this arbitrary. You just make a closed boundary, and you could have a volume in space-time, and you make the integral over this volume. Based on the Stokes theorem, the volume integral can always be transformed into you can cancel one covariant derivative. You can cancel one covariant derivative and have a integral on the boundary. They just equal each other. So in this way, if you choose, now we choose an arbitrary volume, which means in fact you can define a locally property, conserve the property. But we prefer, because energy is globally quantity, so we prefer to define it globally. We need to choose this volume as a special volume. So we choose a boundary, one of the boundary at a special infinity. And then the other two boundaries, one is one slice. As I said, ADM energy is defined based on the 3+1 formalism, which meaning you have lots of slices, with each one is a 3-dimensional space vector have surface. And so if you want to find the relationship between Komar energy and ADM energy, this meaning you have to choose the boundary as slice, because ADM energy is naturally defining for such kind of slice. Then you can try to connect your generalized Komar energy with the ADM energy. So this is why we choose such kind of slice. Then the boundary integral I just showed in that slice, you will become 3 integral on the boundary. One is like for time 1, you have a half surface, and then for the final time 2, you have another half surface. So this is 2 boundary terms, and plus the integral at the boundary at infinity. But since we claim this is a kind of asymptotic flat space-time, the boundary term at the special infinity we can prove is 0, which meaning you only have 2 boundary terms: the integral at half surface 1 and half surface 2. Because this is a minus sign, because the direction of the normal vectors. So in fact, you are proving, this quantity is a conserved quantity at each half surface, which meaning we now, based on the Noether theorem, have a conserved quantity on each half surface. So the K part is then to show the physical meaning of this term, whether it's how to claim, how to prove it is a kind of energy, or it is a kind of maybe momentum or any other conserved quantities. So then this meaning we have a definition. Recall, we're defining the current in this way, which means it's an antisymmetric tensor within here, within the covariant derivative. And the Stokes theorem, you can apply Stokes theorem again for the tensor which is antisymmetric. Transform this integral on each half surface. We have we have the conserved quantity on each half surface, and then we try to transform this conserved quantity from the half surface to the boundary of the half surface, because this is where the Komar energy defining is depending on the boundary of the half surface, or a two-dimensional boundary at a special infinity. It's a little like if you know ADS CFT, you know the boundary information, you know the whole energy of the space-time. Yeah. So.
Sorry, can you say what is asymptotic moment condition here? What's asymptotic moment condition?
Oh, that's a special one. You have a space-like half surface, and space-like half surface, the boundary of this half surface, which meaning it's live in the half surface, but it's a boundary. It's not a null boundary. Maybe I think you guys think about null boundary.
No. I just wonder, say, so now you are considering the spatial infinity, and at the spatial infinity you need the field to have some follow behavior, and I just want to make sure what follow behavior you adopt. And is the follow behavior in Erwa paper or other paper?
No, not the vector is general. As I said, you can choose an arbitrary vector. This vector is arbitrary. But the boundary only constraint on these two vectors. Which
in your previous slide, you mentioned that the boundary term vanish.
Yeah.
When you take Stokes theorem in a cylinder, you claim the boundary term vanish.
Yeah.
And I wonder what is asymptotic boundary condition you
the boundary condition is just like the most fundamental one, which meaning you can write the matrix J mu nu as the Minkowski matrix plus correction terms like in the order of 1 over R, which is the most generic one. Yeah. Later I will discuss this asymptotically condition more detail, because yeah, this is very important.
So deal with the rotation.
Um.
When you deal with the rotation, do we need to assume extra boundary condition?
I think so. Because when you have rotation, your asymptotic condition may be different, because now we require 1 over R. Rotation will give you rotation momentum. We are studying it now. It seems you have to further generalize, what I propose here. But now I guess for most the rotation, it depends on how strong I think because rotation is related to angular momentum or something like this, how strong the angular momentum is. Like for the rotation, based on the Schwarz in the stationary case, the black hole, is too strong. Like it's 1 over R. I guess it may be too strong to obey the asymptotic condition I have here. But yeah, we here I only consider energy. Yeah. Yeah, and then you have a conserved quantity which is depending on the boundary, which is expressed into this. This is look like the same already, with the Komar energy. The only difference, is in Komar energy. Here, Kc is not Kc, Kc is a Killing vector. Yeah, as I showed, But now we can show this is a general quantity, general vector, and it's a conserved quantity. The key part is, how to connect this with some physical interpretation. The things we try to do is, we give it a very generic definition and then try to see how we connect this with the ADM energy definition. And we will see our proposal, how to choose this vector in dynamical case is also very reasonable later, after we figure out their relationship. Yeah, then is what you ask, what kind of asymptotic condition we use. There are two, popular asymptotic condition you can use. One is the York condition. York developed a kind of asymptotic condition used to analyze energy definition. He developed this, most for Komar energy definition, I guess. His asymptotically-flat condition, both put constraint on the J mu and the extrinsic curvature Kij, and also energy density in the rho, and momentum current density Gi. So this is too complicated, and we think his constraint on energy density and momentum density is too strong because it's 1 over R4. We will show, we don't need such a strong condition to prove the relationship. So we give up this constraint on energy and momentum, and only keep his constraint on matrix and extrinsic curvature and transform the extrinsic. Any question? Okay. And the extrinsic curvature can be transformed into the reduced matrix, in fact. So you can also connect it with the matrix. So this is why we call it York-like condition, because we don't use his energy and the momentum constraint. We only use some parts of it, which meaning our condition is even more generic than his condition. York's condition is already, I think, the most generic conditions, but we will find this is not enough because he split the time coordinate and the space coordinate into 2 parts to deal with, which make his asymptotic condition is very hard to deal with. Like he assumed the space derivative of the J mu behave like 1 over R squared, or S squared for infinity, or the time derivative of the Jij, the reduced matrix, behave like 1 over R squared. You will see he don't put any constraints or say anything about the J00 term. J00 and derivative on 0, which meaning it's the time derivative of the J00 term. So he put his arbitrary because when he do his analysis about ADM energy, seems he don't need this condition.
Oh, but that term, I remember that J00, that should be a gauging variable, right? So you can choose different gauge, and we will have different. That's a lapse function. That's why we don't need to put any constraint on that variable.
This is only when you do the 3+1 split formalism. But in general relativity, it will influence other terms, right? Because if you choose different lapse function, then the J0 term will change together. You cannot cancel it. So
what is the definition of R here? Have you choose any specific?
I think it's just choose the condition coordinates, which is x1, x2, x3. Yeah, and the R equals the square root of x1 square plus x2 square plus x3 square. Yeah.
So then you already have decomposed the space-time into 1 plus 3.
Sorry.
I mean, if you choose R to be the square root of x squared, y squared, z squared, then you already specify the 3 plus 1 decomposition.
Yes, because ADM math also based on this spectral coordinates.
Actually, I'll come back to this spectrum.
Okay. Okay. Yeah. Yeah, this is how we depending. Okay.
I would say, what is rho and J here?
The energy density and
In the third line.
Oh, you
The
mean?
equation they got by storage.
Oh, you mean here? Yeah, rho is the energy density.
From the matter or from what?
I guess from the latter, yeah. From the matter. This is depending, I guess, from T mu nu.
Yes.
Yeah. The other side of the Einstein equation.
What is actually the third condition is actually not independent to the other two, because you mentioned you don't need to use the condition for rho and the condition for J. Actually, they have been encoded in the Hamiltonian constraint and momentum constraint. So if we look at the Hamiltonian constraint, we already know there are R3 and Kij in that constraint. sets of the order R squared, R inverse squared.
Uh-huh.
And Kij enter the Hamiltonian constraint with a Kij. So that already becomes R to the minus 4. In that case, rho must be R to the minus 4. So as long as you use the first two conditions, you are using the third one.
Okay, I see.
That's my understanding. May not be correct, but
I don't think so, but we can discuss maybe. No. If from Einstein field equation, for example, you only have you only have second order derivative for J mu nu, I'm right, the matrix, which meaning if your matrix is 1 over R squared, in fact you can only guarantee this is 1 over R cubed, not 4, it's 3, I guess.
Sorry,
I think in the 3+1 splism or in general relativity Einstein field equation, if you consider Einstein field equation, the derivative, the order of the derivative for the matrix, the lowest order is second order, 3.
Yes.
And if you based on 3+1 split, you said you have constraint for rho, then you have a Kij dot 1 order derivative for Kij. You don't have second order derivative. You only have 1 order derivative. Then you still have 1 over R3. So you cannot have this. Otherwise, he will not need to require this. But he will find, only use this condition, he's not enough to define ADM energy or finish his analyze. This is why he requires this extra thing. Yeah, I think you will only have 1 over R3, not have 1 over R4.
We can talk about
Yeah. Okay. So, but later, we will find your condition is too hard to deal with. Although it's very generic, it has less constraints. We require another asymptotic condition. Weinberger does make this very simple. He does assume all the term of the matrix, approach the flat spacetime as special entity in the same speed, which is 1 over R squared for every term. So he just write J mu nu dot alpha e just equal to this, equal to 1 over R squared at a special infinity. So we will firstly use this generic to do the analysis, but then we find we cannot prove they are equal if we don't use Weinberger conditions. So we first try to prove it as generic as we can, but when we cannot make further progress, we have to use the Weinberger. Yeah, this is from our side. And the other important thing, we need to choose this vector C mu in the generic or general Komar energy definition. So which vector should we choose? At the beginning, at the early analyze, we just choose the most generic one because it's an energy definition. So it's very natural to choose the partial T mu, which is the tangent vector of the time coordinate, and plus of.
Just in this slide, these asymptotic boundary conditions are for the 3+1 space-time domain or for general space-time domain. When you write the York-like condition or Weinberg conditions, you are talking about the case for 3+1 space-time or for higher dimension, or also for higher dimension.
No, only for 4-dimensional, 3+1 or 4, yeah. And not for arbitrary dimensional, yeah. If you have higher dimensional, I remember this asymptotic condition is different. They behave different, yeah. You have to choose other volume. And then, so we choose the tangent vector of the time coordinate plus generic corrections. Here we choose n that's bigger than 0, which means it's a kind of asymptotic condition, but it can be very slow to approach. Yeah. So we don't require the stronger. So it's very generic, but later we will specifically define it in the to prove the ADM energy equals the Komar energy. another reason we can do this is, is because this reduced to the K vector in the stationary case. So it's very natural to choose this. And then we begin to do the analyze. This part is a little important. I try to not give too much details because the derivation is too long. We begin from the ADM energy definition based on the York-Light condition, which is mainly these two conditions, and the vectors. Then we try to, because it's asymptotic flat, so at special entities can be connected with the Minkowski matrix. And this can just equal to related to the delta function, which because partial T mu in fact is just it's only true, only have a non-zero term at the zero. It's just 1, 0, 0, 0. So it can also be equal to a delta function which is delta 0, 0 in fact. So then you can transform the delta 0, 0 term, like this term, I guess, into the vector.
Can we choose a coordinate such that the curved black hole also satisfies the Wang asymptotic model?
No, I don't think so. I think curved black hole is the rotation too strong. You have to add another vector or current analysis. Do another project which is generalized to include the momentum. You have to choose you have to have another momentum vector. Like here, although we still not finish the whole work, but because C mu will not only be partial T mu, it will plus like a partial phi mu for curved black hole. Then you will have both energy and momentum.
No, I just asked, previously you mentioned about the Weinberg-like asymptotic boundary condition.
Yeah.
I asked whether curved black hole can be adopted to this asymptotic boundary condition. Can be.
Yeah, I think so. The diagonal term, I think when decrease in the term of 1 over Rm, right? So which means it follows that condition by Weinberg. It's just 1 over R. Yeah. So that's why I think it's okay. But you need to choose special coordinates because some coordinates, will give you like a square root of R, which means 1 over 2, not 1. Decrease the speed more slowly. Like I said, you transform some part into the maybe the Laplace function or the J11 term of the matrix. Yeah. So and then you can transform this, relate this to the vector we're defining in the generalized Komar expression. And then this can be related to the this connection, can be related to the Riemann tensor because of asymptotic condition and some antisymmetric relationship. Maybe I can skip these details. If you are interested, you can read the paper. The paper contains even more details. The final result, nearly final result is something like based on York-Light condition, you will have which is the T mu nu term. This is based on Einstein field equation, or the J mu nu Einstein tensor, which is half of the Einstein equations, and then the Riemann tensor, and then R mu nu. So use the bench identity, I guess. I remember, we can transform this into the antisymmetric of Casimir. Because this Casimir is contract with the Riemann tensor, you can use a bench identity to write this into an antisymmetric derivative for the Casimir, the vector. And then you can use this relationship, you can, because the generalized Komar energy is the antisymmetric derivative of the Casimir. You can have this, the generalized Komar energy and equals the ADM energy plus the Einstein tensor and plus lots of extra terms based on the Lie derivative. Until here, this part in fact is more like some generalized of the some proof in the stationary case. People have realized this even in the stationary case. But this is the important and new things we developed. We can stop here for one moment and let me quickly show this. In fact, from here you can see in stationary case, the ADM energy and Komar energy have relation because in stationary case, Casimir will be a K vector, and these are all about Lie derivative. this Lie derivative is 0 for k vector, which meaning they all vanish, these large terms. But it's a derivative of a Lie derivative, When you expand this out, you must realize this is a very huge expressions. Each Lie derivative is 3, derivative about the matrix, and another covariant derivative will give you maybe another, times another 3. So it's a large expression. This is why when people go to this step in stationary case, they will claim, Casimir is a k vector, and all this term vanish. Then you have stationary case, and you have the Komar energy definition for stationary case. And then they require a asymptotic condition, which is J mu nu reducing the speed of 1/4, as I said, because it's a volume. So if this reduces as 1/4, of course it's 0. So this is how people deal with, this step when deal with this hard part when people deal with the stationary case, and then they prove they equal each other. So until now, there's no. This is you can say this is well known. It's the steps is not written in a single paper, but if you read lots of literature, you can go to this step. And of course, they use k vector. You just replace the k vector and have a little more trouble, but you can go to this step. This is true. So our result naturally reduced to the equivalence relationship of ADM energy and Komar energy in the stationary case based on the York-Light condition. But we use weaker condition than their previous proof for stationary case. But here we want to prove this in the dynamical case, which meaning we will not require this to be a k vector. But now because mu is very generic in fact. It's just the partial T mu plus some any generic fractions to it. Maybe even can be the momentum things you prefer. So to further prove, to further simplify this, we try different vectors. And finally we find, there's a very natural vector and a very reasonable vector to choose. We choose partial T mu, which is the tangent vector of the coordinate, the time coordinate. But in fact, in general relativity, there's no special coordinate. No coordinate is special. You should always have some physical quantity which is independent of coordinates, because you can always choose different coordinates. You can draw the time coordinate in this way. You can also draw it in this direction maybe. Then you have different vectors. So how you define the energy? This is also the hard part. But we find, in fact, ADM mass is based on 3+1 split formalism. In this picture, this blue line is the half surface. We just draw it as a line because each point is the two-dimensional sphere. When you have this, constructions to define the ADM energy, you already naturally choose a unique vector, which is the timelike norm vector of this space-like hypersurface. So the only unique and special vector for such a hypersurface is orthogonal or norm vector. It's T mu. So we find, when we choose the vector as T mu times the Laplace function, I guess the Laplace function here is just like a kind of redshift vector, which transfers the local energy definition or makes the reference to special infinity. So your observer is at special infinity. It's a kind of vector field or observer field, spanned from spacetime to special infinity, and it's just a normal vector group. So when we choose the vector in this way, and we use the Weinberg conditions, these conditions now make it slightly stronger than the York-Light condition. We find, there are two big parts, One is this part we before us just required to be 0. And for this part, it's just 0 because it's stationary case. And now we try to lose both of these conditions. We don't require this, whole things to be asymptotic flat to be 0. We also don't require this to be a k vector, things and to be 0. We just use what we just choose, the norm vector and the asymptotic conditions, Weinberg conditions, to see, what will this be expressed into. After some long calculations, I will not show here. The Lie derivative will become the time derivative of the extrinsic curvature. The extrinsic curvature of the hypersurface label how you embed a hypersurface into the spacetime. Like even internally, it's a flat spacetime, like but the extrinsic curvature can still be curved, non-zero. So this is something like this. And we found that long-term, B derivative can be expressed into the extrinsic curvature Kij, take time derivative minus, the scalar of this, take time derivative and times the reduced matrix gamma Ij. So it can be expressed into this way. And then, we found the four-dimensional Einstein tensor, the other term in the expression, can be expressed into the three-dimensional based on 3 + 1 split formalism. If you are familiar with this, it's not very hard, I guess, to find this. The other term becomes the three-dimensional Einstein tensor, Jij3, minus, the extrinsic curvature and the time derivative and minus K and 0. You can see, these two terms exactly equal each other. But one is plus, one is minus, which means they exactly cancel each other. And only left with the three-dimensional Einstein tensor. So the whole expression based on the Wimberg condition and when you choose the vector as the normal vector times the Gauss function or redshift vector or something like this, the relationship will become, ADM energy equals to generalized Komar energy. Now, this vector become the normal timelike vector minus the three-dimensional Einstein tensor. So then we only need to require this term decreasing, quickly at the boundary, and it's a boundary integral. And we only need this three-dimensional Einstein tensor decrease if we want it exactly equal. The asymptotic condition now becomes you require to decrease quicker than 1 over R3.
Why don't you use the equation motion?
You mean you want to equation motion further simplify this or what?
No, I said, now we want to show that the two quantities equal to each other. They
Yeah.
are only different up
to this term.
Answer, but by satisfying the equation motion, then you directly show they are equivalent. But why you don't directly use the equation motion?
I don't see how could you directly show the equal each other.
Under the equation motion, does this term vanish? Oh, maybe not. You also assume matter field. Is this because you also have matter field?
Yeah, I think I cannot say there's a 0 because this can be raised maybe to momentum density or something like this, matter field. Yeah. Of course, if you assume it's matter field free, maybe you should directly have this to be 0. But you have you have to have some requirements or conditions here. But I prefer to use the asymptotic condition because in the stationary case, they use a kind of a constraint. Of course, this constraint is also constrained on the matter field because you can relate it to that. So you can also say you require the matter field decrease in this way, 1 over R cubed. So in this condition, they are exactly equal. Or if you don't have this condition, you will have this extra term. But now you can see important things I want to emphasize. This three-dimensional Einstein tensor is not a projection of the four-dimensional Einstein tensor directly, because if you project the four-dimensional Einstein tensor to have surface, you will have extra term like the extrinsic curvature. And the extrinsic curvature, in fact, is related to how you embed the hypersurface in the four-dimensional space-time. But now, it's entirely, this relationship is entirely determined by the internal property of the hypersurface. The ADM energy is depending on the hypersurface, and the Komar energy is depending on the normal vector hypersurface. So it's more like, I feel it's more like the two sides of a coin. One uses the reduced matrix of the hypersurface, the other one uses the normal vector of the hypersurface to define the energy, and they are, they are equal each other, except this Einstein tensor which only live within the hypersurface. So this is the relationship we have found. We think it is already very elegant. Of course, you can further study these terms and see whether you can further simplify or interpret it. This is also one project we want to do in the future. But this is the key result. So from here you can see, firstly, we don't need k vector. Secondly, our asymptotic condition is even even more simple, than when they prove the equivalence in the stationary case. Because in stationary case, when Beige prove their equivalence, they require this Jij to be a four-dimensional J mu nu, except k vector. We simplify this because we find the extra lead derivative related to k vector can cancel, the extrinsic curvature part, which makes this four-dimensional Einstein tensor into a three-dimensional Einstein tensor. So we use a weaker condition to prove a stronger result in dynamical spacetime. And yeah, this is the key result of our research. We hope, because the direction of LEGO and so on, people will need to study dynamical black hole, dynamical spacetimes. So we hope, our proof will provide people a generalized Komar expression, which is coherent to study, any dynamical properties in the astrophysics, and hope it will be a useful tool in the future. Yeah, this is research this is the key result of our research. Thanks.
Can we go back to page 12? Yes. So in this work, how you assume that the Einstein tensor in the second term,
yeah,
that you somehow vanish this term with some boundary condition or not?
They just assume it's asymptotically,
So you assume some boundary condition to make the second term vanish.
Yeah.
Okay.
If
then,
this is also how they did, when they proved the station.
Then in the later approach, you do not assume such.
Yeah, we don't. We based on this, but don't assume it. I just say, if you assume this, you can obtain the stationary case people have done 40 years ago.
Okay. Then for this second term, instead of putting some boundary condition, can we just put some energy condition for the T value after you use some equation motion for the second term?
Yeah, they're equal, but we find, this part of, if you use 3 plus 1, you can split it into a three-dimensional Einstein tensor plus some extrinsic curvature terms. The extrinsic curvature term directly cancel this term in dynamical case.
Okay. And
then you have a three-dimensional Einstein tensor left, Jij, as I said. This Jij, based on the Hamiltonian, a 3 plus 1, split formalism and the Hamiltonian constraint or something like this. You can reduce this Jij to, I guess, energy density and momentum density.
Yes.
It's a combination, of it.
Yes, and then my question follows as if we use the point of view of energy condition for the boundary, then would be these two approaches to be equivalent?
I guess, of course. Otherwise, the Einstein field equation will be failed. I think they should equal.
Okay.
But in that way, maybe it's easier to interpret. But you need to do some work. And I think I tried this. I tried maybe for 1 week or 2 weeks, but I find it's not easy to deal with. And I think we already have a good result. We can put it online at least.
Okay, good.
So but I think as I said, this is a further project. Maybe we want to try to do to see I think we are trying to see. This is a very good question. We are trying to see the physical interpretation of this term, because now that's a geometry, interpretation. And the hard part is, in four-dimensional, which can connect to the Einstein tensor with the energy momentum tensor, which meaning you can have a clear, physical interpretation for the, each element, each terms of. However, in Einstein tensor is you don't have such a relationship. So you have to based on the 3 plus 1 split, and the 3 plus 1 split can be complicated. There can be extra term. Like for example, you may have a extrinsic curvature. So if you do this way, you may go back to have extra terms. So it's hard to you need to think about it. It's not so.
In terms of energy, in terms of the energy condition, it might be more simple and physical.
More physical. Yeah. I agree. I totally agree with this. Yeah, but it's just because our paper is long enough, right? And I think this could be a future of maybe a small work. Yeah.
Can you say again? How do you argue that the three-dimensional answer term matters?
Oh, we just put a constraint as it like if you in Bayes condition, when he proves the equivalence, we just directly require asymptotic this term equal to 0, which meaning he require this term. Oh, sorry, he require this second term. J mu 4-dimensional and term reduce 0 quickly enough at special infinity. The tensor reduced to 0 quick enough. And in fact, in Einstein tensor or Einstein equation, the J0I term is the energy and momentum term. The Jij term is the transform between the flux between the momentum. So the Ji0 term, in fact, is a stronger conditions because you have put a strong conditions on the energy and momentum flux, or not flux, energy and momentum density, but we don't need that condition. So although we just move it from J mu to Jij, in fact, I think it's a big change. It's a big difference because I need to put a very strong constraint on the energy momentum. This is also why you can see York, in equation 3, York requires the momentum to be reduced so quickly because I guess he needs the 4-dimensional. This corresponding, in fact, to the 4-dimensional. In the 4-dimensional Einstein tensor is the J0, 0, and the J0I term. J0, I think is strongly related to rho, and then J0I is just Ji, strongly related. But we use other term to cancel this constraint, which this is also why we don't need this constraint.
Another question: when you choose the diffeomorphism vector, you require it to be proportional to the time shift multiplying with a lapse. And it's important that you multiply it with a lapse vector.
You meaning when I choose the vector, and yeah, I think it's important. It's very important, yeah. Now when I explain, it seems it's simple, but when you do the calculation, you have the lapse function or not have lapse function have totally different result. You will have lots of extra terms, maybe 4 or 6. But yeah, you just have to try to do the calculation again and again. You find the extra terms seems is the derivative of the lapse function, and you put it inside, you find it's cancel. And also, only when you have the lapse function, this vector can reduce to K vector in stationary case. Because K vector K mu is just 1, 0, So this is also another reason, I guess. But now you can naturally make it reduce to the stationary case, I guess. This stationary case just become a special case.
But say like if you want to view it in ADM viewpoint,
yeah,
then I will just introduce a correlation, and I may still try to apply the Noether algorithm to this viewpoint. And in this case, a naive choice for the vector is just the time shift thing, the time shift with no extra vectors.
I mean the normal vector.
No, not the normal vector. Say like when I choose the correlation,
yeah,
when I introduce a coordinate correlation, I have a properly defined.
I not quite understand what you are trying to do.
Maybe can you say again what is your vector? Can you say like what is the
my vector is related to the hypersurface you make.
Yeah, but maybe what is the t hat operator? The t hat vector, or what is that?
You mean
It's a normal vector.
here?
Yeah.
It's a normal vector with a half surface. You choose. In the ADM and energy definition, you need to choose half surface. Split the four-dimensional space-time into three-dimensional half surface.
All right. So
Yeah.
this t hat is the normal vector.
Yeah.
Unit normal vector.
Yeah, then it's new unit. When you're defining ADM energy, you already, this is why I said is look at two sides of the same thing. One side is the reduced matrix of the half surface. The other side is the normal vector. And then you have two different energy definitions, but they equal each other because they are conjugate, look like something like this, I guess.
Sorry, but in both of the two definitions, the ADM definition or in your version of Komar energy definition, you are choosing the same vector, almost the same vector.
Same vector with what? It's just a normal vector.
I agree. Well, in ADM definition, it's also not the normal vector.
But the ADM energy don't need vector, right? It's based on reduced matrix. Yeah, it's the matrix on the half surface. Like here. Like here. The ADM energy definition is this. It's only the reduced matrix. The only vector is the non-vector of the boundary. You don't have a timelike vector. It's integral on the boundary, the two boundary. Yeah, there's no vector and the reduced matrix on the half surface.
But secondly, another question, when you choose the data morphism vector, you can also include the shape into, you can also have some component related to the shape, whether that will help or not.
Team you already contain the shape time, right?
No, and when you choose the cosine view, currently you choose the cosine view to be a shape, the left multiplied by the normal vector.
Yeah.
But you can also include the shape into this vector, not the team vector, this vector.
It's already, team you already contains the shaped vector. Team you equals 1 over lap function minus beta I, which is the shape vector over lap function. Yeah. It's already included, I guess. But the shape vector, of course, can be 0 based on which kind of coordinates you choose. The shape vector is used to correct the difference between the normal vector and the tangent, tangent vector of the time coordinate. It's different. As I said here, I have a picture. Yeah. This is the tangent vector of the time coordinate. This is a unit normal vector. This is a shape vector. Shape vector is to label the difference between these two vectors. And we have no, this vector depending on coordinates we choose. And this vector is unit. So the shape vector is used to go from this vector to the normal vector instead. So yeah, the normal vector already contains this effect. I think, yeah.
Okay. Any other questions? No. Then let's send on speak again.
Thanks.
线上有问题。哦，有一个问题。
Seems not very quite related to my Noether second law.
Yeah. Maybe you answer the question.
I'm not very clear what the meaning by Noether second law in dynamical space. I'm not very clear to understand the question. In fact, what is Noether first law, second law? I'm not very familiar with this. Sorry. Yeah, I only know the Noether laws. You have symmetry and the fall is certain the charge. Oh, this if you say surface charge, we have what we defining here finally, in fact is another charge. You can also call it, I guess, a kind of another charge. The inside the integral, I think is just another charge. Yeah. But the Fourier surface charge, yes, I do not understand Fourier surface charge, but it's a kind of another charge. It's related to another charge. It's a generalized Komar energy definition. I don't know whether answer your question or not. But if no, you can either ask again or email to me. Yeah, both is okay. By email here, I guess it's really hard to discuss. Okay, thanks. I guess maybe I don't answer this question quite well.
Okay. Then let's close out this seminar. We do have another seminar from the other group, from particle physics group, downstairs in the fourth floor. But axial cosmology, if you are interested, you can go there.